Newton's method. Administrative questions. Don't forget to submit your project proposal today. So last time we started to discuss the basic ideas of Newton's method, and the problem we first studied is how to find roots of nonlinear functions. And what we did is that we just did a first order Taylor approximation of the function phi, and from that we derived the update rules for the Newton's method. I will. I just don't want to have animations while I'm reviewing this, but then I will. It will be full screen. Okay. Okay. Then we discussed how to do minimization with Newton's method, and the idea here was that we just want to find the root of the gradient of the the function with this Newton method, and that's it. And here you can see the update rules. Then we started to discuss how good is the Newton method. We proved that the Newton step is a descent direction. And then we listed a few problems that it might happen that the Newton method breaks down because we cannot calculate the inverse of the Hessian. It can diverge. It can be trapped in a loop as well. The motivation for Newton method was, another motivation was that we have a function f. We want to find its minimum. We approximate f with the f hat quadratic function. We calculate the minimum of this f hat function, and we move there. Any question about this? So that's what we discussed last time. And the plan for today is to study a bit more the convergence rate. Last time we just discussed this very fast. So let's look at it again. And then we will talk about Newton fractals. And then we start discussing conjugate gradient methods. Questions? No questions? OK. So our goal is to find the root of a function f. Let x star denote this root. And the assumption is that f has a continuous second derivative in x star. And then we know that from Taylor's theorem that if we use a second order approximation, then there's a psi n between xn and x star, right? Such that f of x star is f of xn plus the gradient of f of xn multiplied by this error term plus 1/2 the Hessian matrix multiplied by this squared error term, and we calculate the Hessian in this psi n point, right? You know this second order Taylor approximation. Okay, so let's assume that. So now it's just the one-dimensional case. So f maps real numbers to real numbers. So let's assume that this gradient has an inverse, and multiply this equation with the inverse of this gradient. So this is what we get, that we multiply f of xn with the inverse of this, then we multiply this with the inverse of this, so this cancels, and we just have this term. And again, we multiply with the inverse of the gradient this last term as well, and we got, of course, this expression, right? And now let's move this to the other side of the equation. So we will have that this expression that we had is just minus 1/2 this this term in the right-hand side. And this is the, if epsilon n denotes our error, how far we are from the root x star, then this is epsilon squared. And on the left-hand side, what we have, because of the Newton updates, this is xn plus, so x star, we have x star here, minus xn plus 1, because xn plus is just xn minus the inverse of the gradient multiplied by f of xn. Let me know if you cannot follow me, okay? Or something is not clear, you don't understand something. I remember once I gave a presentation, and at some point I switched to Hungarian, but I didn't notice that. So if something like this happens, just let me know. But it's fine, because I do this back at home in Hungary too. Sometimes I talk English to my parents. And okay, so what's this expression here? This is epsilon n plus 1, right? And what we have is that epsilon n plus 1 is minus half times the inverse of the gradient multiplied by this Hessian multiplied by epsilon n squared. So if this is a bounded term, then we can see that it will lead to a quadratic rate. Okay, so this is what we have proved. And now let's just assume that the supremum it's not right here, so let me correct this. So supremum over all x and y, 1/2 f of y, the Hessian, and over f of x. That's bounded. Okay, so it means that we have a, this is m, and epsilon n plus 1 is just m times epsilon n squared, where m is a bounded quantity. Okay, if we further assume that at the initial point, epsilon naught, which is just x star minus x naught, is less than 1, then we can see that with quadratic rate, epsilon n is converging to 0. So this is a proof of the convergence rate for this very special case when f maps real numbers to real numbers. Any question about this? Is it clear? Okay, later if we have time, we will
Yeah. If it's less than 1, if m doesn't have to be less than...
No, m can be any, right? So
Doesn't have to be less than 1 over m?
which one?
What's that on zero?
Good point. So let's so what I need is that the second step of the iteration we also want
Right. This means that it has to get less.
less, yeah.
Then it will get less forever. That's...
So 1 over m, right? Good. Other questions? Okay, so let's see a few problematic cases. What can happen? So here is a function. So 3-ordered polynomial. And you can check that its roots are in -3, 1, and 4. And we want to find the roots of this polynomial. Okay? So this is what happens if we start from x0, this point. Then the Newton method would converge to 4. We are happy that's a root. If we decrease this a tiny bit, then we would converge to -3 from this point. If we converge this a tiny bit again, then we converge to 4 again. And if we decrease it a tiny bit more, then we would converge to -3 again. And if we decrease this a little bit more, then we would converge to 1. So it can be a pretty messy, right? From which point we will converge to where. Here is another problem. It's again a 3-order polynomial. Our goal is to find its roots. And this is how the polynomial looks like. And let's start the iteration from x not 0. Oops. So we start from here. Then according to Taylor method, we fit a linear first order approximation in this point. We would get to this point. Then in this point, we would fit another first order approximation, and we would come back to this point. So it would just jump from 0 to 1, 1 to 0. So we would never, ever would get to the 0 place of this function. Right? So it means that the starting point is very important where we start the Newton's method. You can see this, right? What happens here? Okay, here is another problem. It might happen that the Newton's method will never converge, except in the root. So if you start from the root, you stay there. But from all other points, you would go somewhere else. Okay, so let's f be the x to the 1 over 3. This is the first derivative of f. This is its second derivative of f. And now the Newton update would be that xn plus 1 is just xn minus f over f prime. And if you calculate this, it will be minus 2xn. So no matter where, if you start from x0, in the second iteration, x1 will be 2 times that. And you just always multiply it. So you would go to infinity, no matter where you started, except if that was 0. Right? And you can check that, indeed, in this case, if you calculate the supremum of this expression, then it wouldn't be bounded. So we had an expression for the for quadratic convergence, but that expression is not bounded in this case. It might also happen, which proves that Newton's method has quadratic convergence rate, but in some cases it can be linear only. So here is an expression. So let the function be x squared, and our goal is to find its root in 0. So the first derivative of f is 2x, the second is 2. Here is the Newton update. So xn plus 1 is xn over 2. So from any point, we would converge to 0, but only with linear rate in this case. And again, the problem here that expression that we had for quadratic convergence, that's not bounded. Questions? Okay, and here is another problem where things can be very bad. So the function is 7x minus the logarithm of x, and our goal is to find the minimum of this function. You can prove that the minimum place is 1 over 7. This is the first derivative of f of x, and this is its second derivative. So the Newton update would be just xk plus 1 is 2 times xk minus 7 xk squared. This superscript should be subscripts. And here is a table that shows the convergence from different starting points. So if we start from 1 here, then what the Newton method does, it fits a quadratic function in this point. And you can see that that quadratic function is a terrible bad approximation, because it would look like, I don't know, something like this, of the whole function. And as a result, in the next step, we would go to point minus 5. So this quadratic function has minimum at minus 5. And you might wonder, hey, at minus 5, our original function was not even defined. But still, the Newton update can continue from there, and you would never converge. Okay, but if you start from 0.1 or from 0.01, then you would indeed converge to the true minimum. Okay, so in this case, the range of quadratic convergence, actually, you can prove that it's this interval, and it's pretty tiny. So you have seen that there are lots of problems with Newton method, but still we love it, because sometimes it can be very fast. Here is a few generalizations. So what we discussed is that Newton method was defined on finite dimensional spaces, but actually you can generalize this to infinite dimensional function spaces too. So for example, you have a function, you have an operator that works on functions, and you want to find the minimum of that operator. So you can define Newton method in Banach spaces too, but then we need Frechet derivatives. And we will not discuss this. How we defined Newton's method, it was just on the n-dimensional Euclidean space. That was the domain. But you can define Newton method on curved manifolds as well. For example, what's the Newton method step on a space of orthonormal matrices, where you define a function on orthonormal matrices and you want to find that minimum? And you might wonder why I want to do that at all. But there are problems where they are important. And if we have time, I might show how to do that. So have you ever had this problem that you have to minimize a function over orthonormal matrices? Or any idea where it can be important? Someone? Yeah, when for some reason your domain is rotation matrices, and you have a function on that. And any classical problem where this is important? Yep. Mm-hmm. And that subspace, yeah. So a classical example is independent component analysis, if you have heard about that, where you can prove that the problem is equivalent to finding an orthonormal matrix that minimizes the function. And then Newton method over orthonormal matrices can be very efficient. Okay, and you can define Newton method on complex numbers as well. So let's discuss a little bit Newton fractals. So here is a picture that I was stealing from Ryan. You remember from gradient descent, if you have a starting point, so from this starting point we converge there, from this starting point we converge there, from this we converge here. And you might think that there's a boundary here, that if the step size is small enough, then from this side, from the boundary, we converge to, say, this point. From this side, we converge here. So this is the image that you should forget if you think about Newton method. It's almost good, but at the boundary, things can be very messy. So let's see. So here, we work on complex numbers. now. So let fz be z to the 4th minus 1. And its roots are minus 1, plus 1, minus I, plus I. So say minus 1 is somewhere here, plus 1 is somewhere here, minus I would be here, plus I would be here. Okay, and the colors just means that points have the same color if they converge to the same point. Okay, so from these points here, they all have red colors. They converge to minus 1. And you can see that here in the boundary, things are quite complicated, right? So actually, they form a fractal, and this is what's called Newton fractal. You can also change color. You can change shadings according to how many iterations you need to converge. So you fix an epsilon, and you count how many iterations you need to get epsilon close to the root. And brighter color means that you need less iteration. So this was plus 1. This is minus 1, minus I, plus I. And you can see that if you start from close to plus 1, then you don't need many iterations. But if you are starting to be far from plus 1, then you need more and more iterations. And again, at the boundary, it just looks messy. Questions? And things can be beautiful, too. So in this case, I just wanted to show you an example where we have 9 different domains, and it can be quite chaotic. Okay, here is another example where black just means that the Newton's method didn't converge. So here the polynomial had roots in plus I, minus 2 over minus 2.3 and plus 2.3. So you can see that this is minus I here, right? This is plus I here. This is plus 2/3, and this is minus 2/3. And what happens, for example, here, that if you start from this point, the center of this black circle, then you would jump to the center of this black circle. And then from here, oops, you would jump back. And so you would be in a loop. And if you say start from here, from this black circle, but not from the center, then you would jump to this black circle here, closer to the center. From that, you would jump back closer to the center. So you would converge to the center, but you would never converge to, so you would converge to this loop, but you would never converge to the roots of this polynomial.
Are those 2 points at the center of the black circle somehow important to this polynomial f?
So, but I couldn't hear your question.
I mean, if you start from somewhere in the circle, you will converge to both points.
So,
It's a loop.
yeah, it's a loop. It's
Somehow related to
so
certain properties of that polynomial f.
exactly, yeah.
So what is it?
So it's very messy how it. So it's we need to discuss chaos theory for that, right? And dynamical systems, so it's not that obvious. No, it's more complicated than that. Okay, so one way to avoid divergence is to do line search. So instead of doing a full Newton step, we can introduce a HK step size If hk is 1, then we do a full Newton step. And we can do a line search to like how we did for a gradient descent, except exactly the same backtracking rules. And that algorithm is called damped Newton method. And how it works is that you start from a point, you do some line search. And when you are close to the local optimum, then the line search parameter actually will become just 1, so you do a full Newton step. But as long as you are far from that, you can just do a line search with a hk smaller than 1 parameter. Okay, so let me stop here and start discuss conjugate gradient methods. If we have time, then I would like to come back to this point, how to discuss the convergence rate of the Newton's method in a more general setting. Any question about Newton methods? Everything is easy? Good. Okay, so if you want to learn more about conjugate gradient methods, then here are a few books where you will find more information about them. So the motivation is that we know that steepest descent is slow. Newton method is fast. But the problem with Newton method is that we need to, when we want to find the minimum of function f, we need to calculate the inverse of a Hessian matrix. Generally, calculating the inverse of a matrix, then that matrix is big, then it can be challenging. So we are looking for a method that's fast, but still it doesn't need to calculate inverse of a matrix, inverse of a Hessian matrix. Is it clear what we want? Do you think it's possible? We will see. Okay, so this is our goal, to accelerate the convergence rate of the steepest descent and avoiding the high computational cost of Newton's method. The conjugate, so I will talk about conjugate gradient algorithms, but first we will discuss just conjugate direction methods. And conjugate gradient algorithm will be a special case of conjugate direction methods. So conjugate direction methods were originally developed for solving quadratic problems. So here is a quadratic problem. We want to find the minimum of this quadratic expression. So Q is a n by n positive definite matrix. B is a vector, X is a vector. Or I could say that equivalently, our goal is to solve this linear equation. Qx is B. How would you solve it? So you have an expression Qx equals B. What do we do? Yes, but yeah, it's a very simple. Yeah, you calculate the inverse and multiply. What if I don't want to calculate the inverse of Q? Because it's difficult. Right, so this is what we are going to discuss now. So if Q is positive definite matrix, then we can do some other tricks. So we will see that conjugate direction methods can solve this problem at most n iterations. Okay, so general conjugate direction methods, they are algorithms to solve linear equations where the matrix of that linear equation is a positive definite matrix. And it's an iterative method because it has n steps. And for large systems, it might be more preferable than calculating the inverse of the matrix or doing some Cholesky factorization and so on. And we will see that these methods can be also solved for finding a minimum of nonlinear functions. And how you might guess that we just see how to, that it can be used to find the minimum of a quadratic function, right? And we will do the same trick that we did with Newton's method, that we will approximate the function at a point with the quadratic function, and we solve, we find the minimum of that quadratic function with this method. Okay, so we will need a few definitions. First definition is Q conjugate directions. So let Q be a symmetric matrix. Here I we don't necessarily have Q to be positive definite, but Q is symmetric. And we say that a collection of n-dimensional vectors, d1, d2, and so on, dk, they are Q orthogonal or Q conjugate with respect to Q if di transpose Q dj, that's 0 for all I and j where I is not j. Is the definition clear? Okay, so in most of the applications, this Q will be positive definite, but for the basic definition, we don't need that. Okay, some special cases. So if Q is a 0 matrix, then any two vectors are conjugates, right? Because it's a generalized inner product that would be 0. Another special case, if Q is the identity matrix, then it's equivalent to the standard notion of orthogonality. One important property that we will use a lot is if this lemma, called linear independence lemma. So if Q is positive definite, and d1, d2, and so on dk vectors are Q orthogonal or Q conjugate, then they are linearly independent. Okay? So let's see the proof. It's pretty simple. So let's prove it by contradiction. So let's assume that there's a vector dk, which is a linear combination of the other d1, dk minus 1 vectors. And then let's multiply this equation, or the transposed of this equation with q dk. Or I could also say that let's multiply this with dk transpose q from left. So now what we have is that dk transpose q dk is, of course, just this expression here. And by the definition of Q conjugacy, all terms here, they are zeros, right? But we also know that Q was positive definite. So this expression must be positive if dk is not 0, but it's also 0, so that's a contradiction. So we proved that if Q is positive definite, then if k vectors are conjugate, then they are linearly independent. Good? So let's move on then. So let's talk about why this Q conjugacy is useful, why it's that important. but let's discuss that after 5 minutes break. So it's good? Okay, so let's see why conjugate directions are useful. So here is our goal. We want to minimize this quadratic function. And we assume that Q is a positive definite matrix. We already discussed, and this has a unique solution. Right? This expression has a unique solution, and that solution is also the solution of this linear system, Qx equals B. So let X star denote this solution. And let's assume that D0, D1, and so on, Dn minus 1 vectors, they are Q conjugate. We already proved then if they are Q conjugate, then they are independent, linearly independent, which means that for some alpha naught and so on alpha n minus 1 scalars, X star is just a linear combination of these Q conjugate vectors. Okay, so this is what we know. Let multiply this equation from the left-hand side with di transpose Q. Then, of course, we got this expression. And because of Q conjugacy, you can see that all terms here, they cancel except the ith term. And this is the only term that remains. Right? And from this, we get that for alpha I is just this expression divided by this expression. So alpha I is this di transpose Q X star divided by di transpose Q di. So far, the only important thing was that these vectors are linearly independent and they are orthogonal. But now, what another property that we can use here is that this Qx star, what's that? That's B, right? So what we have is that alpha I, for alpha I, we have this expression here. And for alpha I, we don't need to use X star. So if you have a Q conjugate system, then we know that X star is a linear combination of the Q conjugate vectors with coefficients alpha I. And alpha I has this simple form. OK? So that's good to know. Another important property here is, so now we just proved that alpha I has this form. And because of that, X star is a linear combination of the di vectors with these coefficients. And if you look at this, we don't need to do matrix inversion, right? You just need to calculate inner products. Okay, and how we make this X star, you can also think of this as an iterative process where in each step we add, we start from, say, 0 and we add alpha I di in each step to our vector. Okay? That's clear, right? So I could write this, that x k plus 1 is x k plus alpha k dk, and we start from x naught 0, and we repeat this iteration. What we are going to do now is to generalize this iteration to that case when x naught can be arbitrary vector. Right? So in this case, x naught has to be 0. It cannot be arbitrary. But let's see how to generalize these ideas for the case when x naught can be any vector, any n-dimensional vector. Okay, so in the previous slide, we had these expressions. We know them. And we will prove the so-called conjugate direction theorem, which is the following. So let this d naught, d1, dn minus 1 vectors be q conjugate. And as we just mentioned, x naught is an arbitrary starting point. So in the previous case, it was 0, but now it can be arbitrary starting point. We will have this update rule for the next xk. We will need this variable to gk, which is just the gradient of function f. You remember our function, right? That was f of x was 1/2 x transpose q x minus bx. And alpha k is, as we discussed, is this expression here. Oops, sorry. Sorry, let me rephrase this. So alpha k will be defined by this expression. And you can see if gk is this, that's the gradient, then alpha k, I can rewrite this formula as this. And if x naught is 0, then this expression is what we had before. So this is like a generalization of the previous case. Can you see that? So if x naught is 0, then qx naught is 0. So we will have b transpose dk. That's what we have here. Okay? And what we need to prove that in this general case, after n iteration, we have x star, the minimum of function f. Is the statement clear? Okay, so let's prove this. Again, we don't need to do matrix inversion here. The proof is very simple. d naught, d1, dn minus vectors, they are independent because they are q conjugate. So x star minus x naught can be, can be rewritten as a linear combination of these vectors, right, for some alpha, not alpha n minus 1 real numbers. As we discussed, this is our update rule. Xk plus 1 is just xk plus alpha k dk. So if we start from x naught, then x1 would be just this expression. Right? X2 would be this expression, and so on. Xk would be this expression, and finally xn would be this expression, which is by definition is x star. And what we need to show is that with these alpha parameters will be just what we discussed in the previous slide. Is it clear what we need? Right, so in the previous slide, we had an algorithm. This algorithm, which uses these alpha parameters here. And now what we do is that we have this algorithm, but instead of that alpha parameters that we set up in the previous slide, we say that let x star minus x naught be this linear combination of the Q conjugate vectors. And we need to prove that these alpha parameters defined this way is the same alpha parameters that we had in the previous slide. And then we proved that this algorithm indeed converges to x star. Okay, so all that left is to prove that alpha k has this form. Questions? Okay, so this is what we already know. So by definition of alpha naught, alpha n minus 1, we defined them this way, that this is just x star minus x. So x star minus x naught is a linear combination of the Q conjugate vectors with these coefficients. We also have that xk minus x naught has this form because of the algorithm. And we discussed that gk is just the gradient of f, which is this expression. We also know that b is q x star, right? X star is the minimum of our function. So we have that the gradient is just q times xk minus x star. So this is what we know. That was easy. And let's use this knowledge to prove that alpha k has this form. We just do the same things that we did before. So we multiply this equation. Oops. This equation here with dk transpose q from the left. Then this is what we get. It's dk transpose q multiplied with this expression. I just wrote that here. And because of q conjugacy, only all terms cancel except this one. Right? Okay, from this, you can say that alpha k is this expression divided by this. Okay? Let's do the same trick for the second equation. Now dk transpose q multiplied with this vector. Again, it's just this expression. And because of q conjugacy, this is 0. Right? dk is orthogonal to q orthogonal to these vectors. Okay, and now let's continue with this expression. We can rewrite x star minus x naught as x star minus xk plus xk minus x naught. And we already know that if I multiply this expression with dk transpose q, then it will be 0. So what we have is that dk transpose q multiplied with this expression is just this expression here, right? Only this guy remains. And from this, so we continue from this expression, right? We just prove that dk transpose q x star minus x naught is this expression here. And finally, the last step is that we know that q times xk minus x star is gk. So I write minus gk here. And this is what we had to prove. So it's very simple. You just have to multiply everything with dk transpose q. And that's it. Questions? Yes? Very good point. So we will come back to that. Right now it's just we assume we have that, and for any kind of set, this works. So Q by definition is always symmetric. That's our assumption. Otherwise, it would be difficult. So then it wouldn't behave like an inner product. It wouldn't be symmetric. So by assumption, Q is always symmetric when we talk about Q conjugate vectors. And in this example, we also assume that Q is positive definite. There are so-called bi-conjugate methods as well that could generalize this a little further, but we are not going to discuss that. Yes?
Do we assume that alpha k is, say, the projection for the direction of the bk? Some kind of...
Yeah, it's like a projection because we have an orthonormal system, but it's a generalized orthonormal system where the inner productive is defined with d I transpose q dk. But yeah, exactly. It's like just a linear projection using this inner product. Okay. So here is another motivation for Q conjugacy. Again, our goal is to minimize this function. And because these vectors, they are Q conjugate, then for any x, x minus x naught can be rewritten as a linear combination of these vectors. And of course, this function here is f of x. So using this definition, x is just x naught plus this expression. So f of x is 1/2 x naught plus this expression transpose q, and so on. And if you use the Q conjugate property, then you can see that f of x can be easily rewritten as a constant plus n independent one-dimensional problems. So here you have to minimize this in alpha j. So we have n independent optimization problem where the variables are alpha j's, but they are independent from each other, these optimization problems, so you can solve them separately. Right? So and if you have an n-dimensional optimization problem, but each coordinate are independent from each other, then it's just easy to solve. Good? So we will come back to that question, how to find these d naught dk minus 1 vectors. But first we will need another theorem, which is called the expanding subspace theorem. So let bk be the span of these, be the span of k vectors, these Q conjugate vectors. And we can show, that's a very important property of Q conjugate, of conjugate deduction methods, that if we run this algorithm that we just discussed, that xk minimizes this objective function over this x naught plus this bk subspace that we defined here. Or I could also say that xk minimizes this function f over this line, xk minus 1 plus alpha dk minus 1. So here alpha is the parameter that we need to find. So can you see that? So again, our goal was to minimize function f. We already discussed the algorithm, and at the k steps of the algorithm, you can prove that the algorithm minimizes the function f over this set x naught plus bk, where bk is this linear space. Okay, formally what happens is that the algorithm calculates the minimum of our function f over this line, or equivalently I can say that the algorithm calculates the minimum of our function over this set. And of course, in the nth step, this is the n-dimensional Euclidean space. So we minimize this function. Okay, so this is formally the theorem. So let d1 and so on, d naught and so on, dn minus 1 be the Q conjugate vectors. We start from an arbitrary starting point. This is our update rule for xk, and we discussed that alpha k is chosen with this update rule. And then I just copied the previous equations. Then xk is the solution of this optimization problem and this optimization problem. Okay. So the proof is a little bit of calculations, but one thing that we can immediately observe is that it's enough to show that xk minimizes f, our function, on this x naught plus bk subspace, because this subspace contains this line. This is how we defined bk. So again, remember that bk was a span of the first k conjugate direction. You can see that we have, for x, we have this update rule. And because of that, x naught plus bk contains this line. Okay, and the main idea is that all we need is to prove, because f is strictly convex, that if we calculate the gradient at the point xk, so that's denoted by gk, right? We just need to prove that this is orthogonal to this bk subspace. If it's orthogonal to that, it means that we optimize our function over this subspace, because there's no projection of the gradient to that subspace. And this is an explanation what happens here, that we say we were at the point x k minus 2, we move to x k minus 1, and then we move to xk, where in each step we just add, so here we added alpha k minus 2 times d, k minus 2, and here we added to xk minus 1 is dk minus 1 times alpha k minus 1, and so on. And what we need to prove is that gk, the gradient at xk, is orthogonal to this subspace here. Okay, so that's all we need to prove this. gk is orthogonal to this bk subspace. So the proof is going by induction. So we assume that we proved for k, and we have to prove it to k plus 1. And we start from k equals 0, and then it's easy to check that the theorem holds because b naught isn't the empty set. And now we assume that we have proved that gk is orthogonal to subspace bk, and we need to prove that gk plus 1 is orthogonal to bk plus 1 as well. So it's just a simple calculation. This was the update rule of our algorithm, and gk is the gradient. So therefore, at k plus 1, gk plus 1 is, just use this q times xk plus 1 minus b. Now we can substitute the update rule, and we have that gk plus 1 is this expression minus b. Okay, and I can rewrite this as qxk minus b plus alpha k q dk. For this, we have that this is just the gradient. So what we have is the gk plus 1 is the previous gradient plus this expression here. And the proof has two steps. The first step is that we will prove that gk plus 1 is orthogonal to dk. And in the second step, that we will prove that all the other di vectors where I is less than k, they are orthogonal as well. Oops, I is less than k. And that's all that we need. So remember that our goal was to prove that gk plus 1 is orthogonal to bk plus 1, where bk plus 1 is the subspace spanned by the first k plus 1 conjugate vectors. Okay, and everything is very simple. This is just what we proved in the previous slide. This is the update rule by definition for alpha k. So let's just multiply this k plus this equation with dk transpose. So we need to prove that gk plus 1 is orthogonal to dk. How do we prove? We prove that its inner product is 0. So let's calculate the inner product. This is the inner product. Oops, dk transposed. We know that for gk plus 1, we have this equation as a rule. And now you just substitute the alpha k update rule here, and we prove that this is 0. Who cannot see if you put alpha k here, then this will be 0? Who can see it? The union is not the whole class. Okay, if you cannot see, then I don't know, at home spend 3 more seconds on it. Okay, so we proved this. All that left is to prove that gk plus 1 is orthogonal to the other conjugate vectors where I is less than k. So we just proved that this is orthogonal to dk. Okay, so we have proved this line, and by our induction assumption, we know that gk is orthogonal to bk. And we do the same thing, that we want to prove that this is orthogonal to this, so calculate its inner product and prove that that's 0. So the inner product is di transpose multiplied by gk plus 1. We have this update rule for gk plus 1. So we get this. And now it's just di transpose gk, which is, how big is this? This is 0 because of the induction assumption. And this is 0 because they are Q conjugate. So we are good with this. So we proved that gk plus 1 is orthogonal to all the i's when I is less than k. So this is what we wanted to prove. Gk plus 1 is orthogonal to the subspace bk plus 1. So this is a corollary of this, that so we proved that gk is orthogonal to bk. We also proved that since bk is a span of these Q conjugate vectors, of course gk is orthogonal to each of them. B naught is the empty set, and then it's increasing this subspace till, and the nth step is the whole n-dimensional Euclidean space. And since xk minimizes f over x naught plus bk, that's just we proved. In the limit, so when k is n, xn minimizes f over the whole space. Okay, so this is an illustration of what happens, that say at step k, we minimize f over this subspace here. Then in the next step, we move to xk plus 1 with our update rule, which is actually the minimum of our function over this subspace, which is bk plus 1. Right? And then we move to, say, the third direction, this, and at some point we will find x star, which is the minimum of our function. Okay, so these are the this was the conjugate direction method, and now we are going to move on to the conjugate gradient method, where we will answer that question, how to get these conjugate directions. So far we just assume that they are given, and we will use the gradient vector. That's why it's called conjugate gradient. We will use the gradient vector to generate those conjugate directions, and then we will show how to use these ideas to optimize general nonlinear functions. So I think I stop here, and we continue with this next Tuesday, and we also discuss quasi-Newton methods. If you have questions, come to my office hours, which is after this lecture. Yep.
How to prove that xk minimizes f